This is the second of the videos on Introduction to Feedback. This video focuses on why we might want to use feedback. We're going to assume that students are familiar with the concept of open loop, and that was covered in video 1. And in particular, we're going to assume that students understand the weaknesses of open loop control. And also, we'll assume that students can do block diagrams, and they can look at the other videos if they need to revise that. This video is going to look at how we deal with uncertainty. You'll remember looking at video 1 that it was demonstrated that uncertainty in estimates of gain and disturbances are what caused the failure of open loop. So what are the weaknesses of open loop control? Why can't we control car speed with our eyes shut, that is, without being able to look at the speedometer? Or why can't we control the temperature of a mixed flow without a temperature sensor, or for example putting our hand into the flow to monitor it? Why is unmonitored cooking likely to fail? Here's the answer. All these systems lack a measurement or observation. We've no way of measuring the output, observing the output, and seeing is the output what we actually want. And so we can't check what the system is doing. And that was the fundamental weakness of open loop control. There's no check in the system, no measurement, no observation, no way of knowing is the output correct. Without observation, we do not know whether the behaviour is correct, and hence we've got no information we can use to update our system input. Here's an example then. How do we as humans get the temperature of a shower correct? Let's go through this step by step. We turn on the hot tap to get a reasonable hot flow. Then we turn on the cold tap, probably about halfway, be a bit of a guess. Then we wait about 20 seconds and monitor the temperature. Have we got the right temperature? What do we do next? If it's too hot, we open the cold tap a little bit more, and if it's too cold, we close the cold tap a little bit more. And then we wait another 10 seconds and monitor the temperature. When we monitor again, if it's too hot, we open the cold tap a bit more, and if it's too cold, we close the cold tap a bit more. And then again, we wait about 10 seconds and monitor the temperature. Now the key thing here is you'll see there's a loop. We're going to keep iterating round this checking, turning the tap on, monitoring, changing the tap again, monitoring, and we'll keep doing this iteration until we are happy. So what's the summary? We've got a key role of monitor and then apply an adjustment based on the observation. So we're observing the output, and based upon what we observe, we're making some adjustment to the input. So there's two key things in there, an observation, and then the input depends upon that observation. What about getting the speed of a car correct? So how do we do that? We depress the accelerator, the expected distance required, and then we're going to wait about 5 seconds and monitor the speed. Is it okay? If we're going too slow, we'll depress the accelerator a bit more, and if too fast, we'll lift our foot off the accelerator a bit. Wait another few seconds, monitor the speed again. Again, if we're too slow, we depress a bit more, and if we're too fast, we lift our foot off the accelerator slightly. Wait another few seconds, monitor again. And you'll notice once more, we've got this sort of loop, where we're going round and round, doing the same monitor, adjust, monitor, adjust. So the key thing here is monitor the speed, and then apply adjustment to the accelerator, or the input, based upon that observation. How about tuning an instrument for anyone there who's a musician? How would we tune a guitar? Well, you would pluck the appropriate string and your tuning fork and listen for a difference in tone. Are they the same? If the frequency of the string is too low, you'll tighten the string a bit, and if it's too high, you'll loosen the string slightly. And then you'll pluck the string again and the tuning fork again and listen. Again, if the frequency is too high, you'll tighten the string. If the frequency is too low, you'll tighten the string. If it's too high, you'll loosen the string. And again, you'll see there's this iterative process of adjusting the string, listening again, adjusting the string, listening again. So once more, you notice the key role of monitoring what the output is doing and then applying an adjustment based on that observation. So in summary, humans control systems using a very simple strategy. We have an iterative procedure of monitor what the output's doing, apply adjustment to the input based on what we've monitored, monitor again, adjust again, and we keep going round and round and round continuously. Monitor what it's doing, make an adjustment, monitor, adjust. What's the weaknesses then of human strategies? Well, let's imagine the level in the tank has to be maintained accurately all year round, 24/7. Or what if the temperature has to be maintained at 400 degrees by modifying a tap that's only 4 yards from the object, which is at 400 degrees? Or let's look at a chemical process which has got 10,000 different outputs, which must all be monitored and controlled simultaneously. And what do you notice? Humans get bored very easily. We're not good at doing things that have to be done 24/7 all year round. We make mistakes if we have to do repetitive tasks for long periods. We're not good in hostile environments. Things like 400 degrees really do not work well for human beings. We're likely to get killed. Or we also can't deal with many different things simultaneously. So if we have lots of simultaneous tasks, we just can't do it. Humans are expensive. We can't deal with fast timescales, and we have many other weaknesses. So what you notice is though humans are quite good at control in principle, there are many engineering systems where the output needs to be controlled, and humans really are not the best people to be doing it. So, what do we need? We need to automate this monitor, adjust iteration. So humans are good at the concept of monitor, adjust, but we're not necessarily good at the implementation. So in order to do this automation, we need to understand better how humans are actually doing the adjustments. So the monitoring we can get, but how exactly are humans doing this adjustment in this iteration? If we can understand that, then we can automate it and get a computer to do it in place of us. So let's represent exactly what's going on. Now I'm going to use a little tank here just to illustrate. So imagine we've got a tank level problem. So we've got a tap here, so we'll do a tap, there it is. So there's fluid coming into this tank, and what we want to do is imagine what's actually happening. So I'm going to draw a rather beaky human here. There he is. Now the human is going to monitor, that's what the arrow is. If I use maybe a slightly different colour, he's going to monitor the output depth. Now based upon what they've seen, now you can have a rather bendy arm here because I'm not much of an artist, but there you go. He's got a really bendy arm, there's his hand. Based upon what he sees, the human is going to adjust that tap. Now there's one other thing. Coming in here, we're going to have a target. So that's a sort of schematic of what the human's doing. They're monitoring the depth, they're comparing the depth, I'll put a question mark here, with the target depth, and based upon what they see, they then do something with their hand to the tap to get the level right. Now how can we represent that in a different way, which is a bit easier to implement? So this is how we might do it. I'm going to draw a box here, and this box is to represent the human head. That's us thinking. What's coming into this box? We've got a target coming in, and we've got the output coming in. So you can imagine that information is coming into the human head in some means. We are then deciding an input, I'll call that U. That input U is going into the process. Output of the process comes here, and then the key thing is you see that output is what we're actually feeding in here. So you'll notice we've introduced this concept of what's called a feedback loop. Okay, so we're measuring the output and we're feeding back the output into our sort of question mark, our box here, and we're using that to decide what the input should be. So this sort of schematic block diagram represents roughly what is happening. So some interim conclusions. For many systems, it's important to control the output to a specified value, irrespective of the uncertainty in the model parameters and external disturbances. Humans manage this by using a monitor and adjust iteration. And this process is called feedback. That is, we feed back information on the output and use this to influence the input. So that feedback path was what we demonstrated on the previous schematic, and we will develop in the next few videos. Now, just a few warnings. What if it goes wrong? This feedback path can be very powerful. However, what happened at Fukushima with the nuclear reactor? You may have heard of the Tacoma Narrows bridge collapse. What happens if you have exothermic reactions? Okay, and that can happen when you have oil or petrol in engines and other places. What happens if you have something like an inverted pendulum, and that can happen with rockets and segways, or positive feedback through a microphone and an amplifier? The key point to notice here is all these systems have a feedback loop, but if that feedback loop goes wrong, then the system can explode or crash, or something disastrous can occur. So getting that feedback loop right is critical to achieving performance and safety. It's not enough just to say, we put in feedback and everything will be hunky-dory. If you don't put in the feedback correctly, then things will be worse than without feedback. So, what's the key issue which we're going to develop in the future videos? Feedback changes the behaviour, and this can be for better or worse. So just because you've included feedback doesn't mean things will be better. There is a need for systematic design to ensure the resulting behaviour is better. Open loop typically fails to deliver the desired target output, whereas closed loop can do so because we've got this monitor adjust sort of iteration. But we need to know how exactly does it do this? Can we quantify exactly what the human's doing when they're doing this monitor adjust? Can we put some mathematics in there to make sure we do it well? And there's another warning at the bottom. The introduction of feedback implies increased cost, both in the modelling, the design and the components and power, because we need components to do the measurements, and these cost more money, and we also need to put in the wiring and the other parts to construct this feedback loop. And we also are more vulnerable to instability. We can get things wrong and make things worse rather than better.